Hello, my name is Miko Stulajter, and today I'll be presenting on Wino 3 with third order Runge-Kutta with non-homogeneous velocity on a non-uniform grid. My advisors are Dr. Ricardo Carretero at San Diego State University and Dr. Ronald M. Kaplan at Predictive Science, Inc. Let's first introduce what evection is. So linear evection is an important classical problem. It's used in many fields, including physics, in computational fluid dynamics, and engineering. The 2D evection equation is a partial differential equation. And here, these two graphs kind of represent what evection does. We want to take this box initial condition and evect it in the direction of the arrow. And we also provide a 1D slice of this box showing that this box is a shock initial condition, which is a little bit more difficult to evect correctly. The central question with evection is, how do you approximate the evection terms? We want to minimize the error, but we also don't want to increase the computational cost too much. So we'll look at two schemes specifically. The first is the commonly used first order upwind scheme with first order forward Euler time stepping, and the second scheme is a third order weighted non-oscillatory scheme with a third order total variation diminishing Runge-Kutta time step. So let's now introduce our time schemes. So the first is the first order forward Euler. It's the most basic explicit method for time stepping, and it's given by this one simple equation, which is done every time step. The third order total variation diminishing Runge-Kutta is a little bit more complicated and a little bit more computationally intensive, and it requires solving these three equations each time step. But the bright side is total variation diminishing means that no new extrema are created each time step, which is good for having higher order of accuracy. Now that we've introduced our time discretization schemes, let's take a look at our spatial discretization schemes. So first we're taking a look at the first order upwind scheme. So here on the left we show what the 1D upwind scheme looks like, where u is our function value at x, a is our velocity, and x is our spatial location. From these equations we can see in 1D that upwinding is a fairly small stencil with only 3 function values required. Here on the right, we show what happens to our box initial condition after one full rotation through our domain, and we see that our box turns into a blob, having diffused pretty badly just after one rotation. This is bad given that evection should have no diffusion. Now let's take a look at our other spatial discretization scheme, Wino 3. So here on the left we show what the stencil is in 2 dimensions. We see that in x and y the stencil looks exactly the same, requiring 5 function values at u, 6 velocities, and 6 dx values. This stencil is much larger than what the upwind scheme was. Here on the right, we show what happens to the same box initial condition after one full rotation. We see that some definition of the box is lost, but much less than what happened with upwinding. We can still see that the box is there, keeping the main amplitude the same in the center. Now that we've introduced both schemes, we can take a look at order of accuracy. So we use a Gaussian initial condition with constant velocity and a uniform grid for our order of accuracy testing, and we found that upwind is first order accurate, while Wino 3 is fourth order accurate. We also took a look at a box initial condition and found that since it's a shock, order of accuracy breaks down, but we were able to look at a qualitative comparison between Wino 3 at upwinding and found that Wino 3 performs much better, being able to keep the area in the correct place after one rotation and having the correct amplitude after one full rotation, unlike upwinding. We also took a look at non-uniform grid and non-constant velocity and found that depending on your initial conditions, they could also impact your accuracy.